Hello students, Stride here again. Today we're going to be doing section 11.3 Acceleration notes. Acceleration is going to be dealing with changes in velocity, another key aspect of motion. Our definition for acceleration given to us here: the rate at which velocity changes is called acceleration. And acceleration can be described as changes in speed, meaning you can be speeding up or slowing down. It can be changes in directions, or both might happen at the same time. And it is a vector, which means, again, means we have to have a direction. Acceleration applied to any change in velocity. As I mentioned a little bit ago, it can be positive changes in speed or negative changes in speed. It can be speeding up or slowing down. When things are slowing down, we use a special term, talk about deceleration. Free fall, another key concept. Movement of an object towards the earth solely because of gravity. When we measure velocity, it was measured in meters per second. Acceleration, then, is meters per second per second. We typically write this as meters per second squared. I mentioned earlier the free fall. When things are free falling near the Earth's surface, we always use 9.8 meters per second squared. We give this a special symbol, G. Acceleration due to gravity is 9.8 meters per second squared down. As an object is falling, as illustrated here, a pebble falling down the well, every second it increases its speed 9.8 meters per second. So at time 0, we had a speed of 0. 1 second later, it has speeded up to 9.8. 2 seconds later, it speeds up another 9.8, so that's going 19.6. 3 seconds later, as it's hitting the water here, it's speeded up another 9.8, so at that point it's moving at 29.4 meters per second. Changes in direction are also acceleration. So even if we're moving at a constant speed, if we're changing directions, we are accelerating. Example here, riding a bicycle around the curve. Anything that's constantly changing directions, like a merry-go-round, a carousel, we are constantly accelerating. It's an example, constantly accelerating because it's constantly changing directions. Accelerating, direction is constantly changing. So sometimes speed and direction both will change at the same time, such as a car moving down a winding road. So moving on this winding road, it's going to be experiencing acceleration. Car may be speeding up, it may be slowing down, but as long as it's changing that direction, we know it's accelerating. But both may happen at the same time. Another example, both happen at the same time. Roller coaster is going to be speeding up, slowing down, and it's changing directions at the same time. Constant acceleration, what we'll be working with most of the time, is a steady change in velocity. Things speeding up, slowing down at the same rate over a longer period of time. One example we may see of a constant acceleration is a jet aircraft taking off. We're going to have a fairly constant acceleration as it takes off. Here we're going to be looking at calculating accelerations. So we calculate acceleration for straight line motion by dividing the change in velocity by the total time. So that formula I'm going to be using a lot of is acceleration equals delta V over T. So delta V stands for change in velocity. It's our delta V. Our textbook will use a slightly different version of the formula, but as I go through some problems with you, we'll be concentrating using this version of it. Here's the textbook's formula. Acceleration equals change in velocity divided by total time. So change in velocity again is the delta V. So all that happens to be is delta V equals V sub F minus V sub I. And that's where they came up with this part of the formula. We'll be using the delta V a lot. Key concept here, if the velocity is increasing, the acceleration is positive. If the velocity decreases, the acceleration is negative. So by knowing if it's speeding up, slowing down, we can tell if acceleration should be a positive or negative, or if acceleration is given to us, we can tell if it's speeding up or slowing down by deciding if it's positive or negative. A couple examples given to us here. Coasting downhill on your bicycle, your velocity is increasing, acceleration must be positive. If you keep coasting on level ground, you're going to be slowing down, and the acceleration is negative. As I mentioned earlier, acceleration, a vector, velocity, a vector. We also had displacement in section 1. And if we're looking at straight line changes, either same direction or the opposite direction. If they're going in opposite directions, we're going to subtract. If they're going in the same direction, we're going to add. So we can still combine vectors using vector addition. Example problem, calculations, ball is rolling down a ramp, starting from rest after 2 seconds. Its velocity is 6 meters per second. What is the acceleration of the ball? So like always, we start and we write down some information. Time equals 2 seconds. Velocity after the 2 seconds, its velocity is 6 meters per second. We use the symbol VF for that final velocity, 6 meters per second. It started from rest, that means VI is 0 meters per second. And when we know VF and VI, we can get delta V, our change in speed, which is going to be 6 meters per second. And then to find A, what we're trying to find, what is its acceleration? A equals delta V divided by T, which is delta V was 6 meters per second, divided by 2 seconds. Remember, we can't cancel the seconds because they're both on the bottom. What we're left with is meters per second, which is our proper units. Do a little division, and we get 3 meters per second squared. And we want to put a direction with it, which in this case is down the ramp. Down the ramp. Now, always get the direction with the acceleration. Here we'll go through what the author of the textbook did. Again, they wrote out some information, a Try to figure out what. They came up with a formula. They substituted into the formula and did a little calculation, getting the same answer. Always think about if it's reasonable for many situations, relating it to the acceleration due to gravity. As it's going down the ramp, it's got to be less than the acceleration due to gravity. Makes sense. Other one, car traveling at 10 meters per second starts to decelerate steadily. It comes to a complete stop. So its initial speed was 10 meters per second. Its final speed is 0 meters per second. Meaning delta V is going to be, in this case, negative 10 meters per second, because it is slowing down, so we get that negative. And then they told us that time was 20 seconds. Our formula, we're trying to find A, and A still equals delta V over T. Delta V is negative 10 meters per second divided by 20 seconds. Well, division, and we get a 0.5, so A is negative 0.5 meters per second squared. And we don't really have a direction listed in there. When that happens, I just like to say it's going forward. Good, here's what the book's doing. Essentially, same work I did, writing it out a little different. Didn't put a direction on here, and they should have put a direction on here. So, forward. Another example. Airplane travels down the runway for 4 seconds, so that would be our time, 4.0 seconds. So its acceleration is 9.0 meters per second squared. Positive acceleration means we know it's going to be speeding up. And they want to know what is the change in velocity, so we want to know what is delta V. So we go to our base equation. Acceleration equals delta V over T. Trying to find delta V. And remember, anytime we're trying to find that thing up on top, if you multiply the other two, you'll always get there. So delta V equals A times T. In this case, delta V equals A 9.0 meters. When we write that out, make it per second, and multiply by the time of 4.0 seconds. Seconds cancel seconds. And then we do a little multiplying and get 36 meters per second. Now, when we do a change in velocity, we do not need to worry about a direction. But again, 36 meters per second means it is speeding up. Delta V sign always will match the A sign. And their work, now they wrote it out, their same answer. Child drops a ball from a bridge. Ball strikes the water 2 seconds later. Got our time, 2.0 seconds. We got a falling object, so our A is that G value we had earlier at 9.8 meters per second squared. It's going to be speeding up. If it dropped the ball, that means initially its speed was 0 meters per second. And we want to know the final velocity when it hits the water. Now, anytime we're trying to find the final velocity or the initial velocity given the other one, the way I'm going to have you do it, we first try to find delta V. So our formula, A equals delta V over T. It's like before, rearranging it, we get delta V equals A times T. And delta V, A, 9.8 meters per second times 2.0 seconds. Do a little multiplying there, and we get 19.6 meters per second. Yeah, that ball was going to be speeding up, so it started at 0. So its final speed is going to be the 0 it started at, and it speeded up 19.6 meters per second, making our final speed. And they ask for velocity, so that means we're going to need a direction. 19.6 meters per second down. Here they rounded it to 20. Same work though. Fourth example. Boy throws a rock straight up in the air. It reaches its highest point at the rock after 2.5 seconds. How fast was it going when it left his hand? So time, 2.5 seconds. We want to know how fast it was going when it left its hand, so we're trying to find v sub I. The final velocity, when it reaches the top of its arc, as it's going up and up and up and up, it's going to be slowing down. So when it finally gets to the top, it's going 0 meters per second. Like the preceding problem, we are first going to try to find delta V. We are again dealing with essentially a falling object. Our acceleration is still g at 9.8 meters per second squared. That's actually our A. So again, we want to do A equals delta V over T, meaning delta V equals A times T. So delta V equals 9.8 meters per second times 2.5 seconds. Seconds divide out seconds. And 9.8, calculator work, times 2.5 gives us 24.5. Only got a couple digits there. I'll just round it to 25 meters per second. Yeah, it started at 0, or it ended up at 0, so that means it started at 25. So because the VF was 0, the VI is going to be the same as this. So VI is 25 meters per second up. Here they did a little talk about putting a negative in front of it, indicating it's in opposite direction of the acceleration. I prefer the positive and then put the direction on. It's more understandable. Yeah, we do a little bit of work on distance times. We done a little bit of work on distance time graph earlier. Here we're going to be looking at speed time graphs. When we had a distance time graph, the slope was the speed. With a speed time graph, the slope is the acceleration. When we're dealing with slope, we're still going to think slope is rise over run. We've done some work with that before. And we can use a graph to calculate the acceleration using this slope. When we graph, we always want to put the speed on the vertical axis and the time on the horizontal axis. Oh, here's a graph illustrating a 4 meters per second squared. The slope of this line is 4. Then we go up 4, we're going over 1, like right here. Up 4 over 1. That gives us 4 meters per second squared. If we have constant acceleration, we're always going to get a straight line. And the slope of the line is the acceleration. Now, if we have a speed-time graph, and it's accelerating, the line is not going to be straight, it's going to curve. If a line slopes downward, represents deceleration. And the slope is negative. So here's a line going down, got a speed-time graph, so got a deceleration, and the slope of that line is going to be its speed. When it was going this way, it means it was going at a constant speed, no acceleration. As I mentioned earlier, on a distance time graph, we get a curved line. We call that a non-linear graph, and we get some type of curve connecting the points. Here's an example, distance time graph. Because this thing is curving up like this, when it curves up, that means we've got positive acceleration. Positive acceleration. If that line, I'm going to back up to that one more time, if that line happened to curve more like this, that's going to be a negative acceleration, negative A value, because it's slowing down. Another phrase we use, instantaneous acceleration, how fast the velocity is changing at a specific instant. So sometimes acceleration does change, and instantaneous acceleration is at a given time, because acceleration rarely constant and rarely in a straight line. So lots of things are changing all the time, and the instantaneous acceleration is what's happening at a given moment. So, some quick review questions. What is acceleration? And you should recognize that as the rate at which velocity changes. Some of the other ones, the rate at which displacement changes, that is velocity. The time an object's velocity increases has really nothing to do with acceleration. The rate at which speed increases is related to acceleration, but it's not a complete definition. So, rate at which can accelerate from 0 meters per second to 28 meters per second. I'm not going to write everything out on this one, but we'll quickly get a few things. We know delta V is 28 meters per second, how much it speeded up. If I'm trying to find acceleration, we're going to have delta V over t. I'm just going to put this over t, which is 4 seconds. We divide and we get 7 meters per second per second, meters per second per second. So, what is the acceleration? So here, none of these answers are actually right, but they're going to expect to be. They forgot their little exponent of 2. And C is definitely not right. So, doesn't have a right answer on this problem, but again, it should have been 7 meters per second squared. If you were to sketch the displacement of a distance-time graph and a speed-time graph for an object experiencing constant acceleration, what would they look like? So if a displacement time graph and a speed time graph with constant acceleration, the speed time graph would have to be linear. the displacement time graph would be nonlinear or curved. So both graphs will be linear, not true. Both graphs will be linear, not true. Both will be nonlinear. And there's the one. One's going to be linear, one's going to be nonlinear. Which the following is an example of negative acceleration, and negative acceleration is going to be slowing down. So if we go from 0 to 20, positive acceleration slows from 20 to 5. That looks like a negative acceleration. So we should get a B. And we do, slowing down. Acceleration at a specific point on a distance time graph is A, and at a specific point, and that's what we had a bit ago, instantaneous acceleration. Quick true-false question: if an object experiences a steady velocity change in a straight line, it is undergoing constant acceleration, and we say that is true. That's what that means. So that completes our 11.3 notes. That's all for now. Till next time.